For this project, I programmed and built a fully automatic Resin 3D print farm. This time not with a PLC, but through a Teensy controller communicating with a Windows-based controller. Communication to each printer is through MIT's new SDCP protocol that uses a real-time TCP WebSocket connection to read and write data. I also mechanically designed a new way for how the gantry and the grabber interact with the printers. The main problem is there is no existing documentation for resin print farms, at least not in this scale. There is for normal FDM printers, but build plates from resin printers works completely different. One of the first engineering challenges I faced when designing the gantry was deciding how deep to place it towards the printers. In the early design phase, I planned to position it towards the back of the area to make room for the grabber axis in the front. But lifting a full capacity printed part, including the build plate along with some kind of grabber mechanism, quickly showed problems with weight distribution. In this extended state, it created too much stress unless I added a large support structure. So instead, I moved the gantry to the front, then placed the grabber axis to the side of the vertical axis. This gave a much better load balance, with the static load in the center, the lifted weight in the front, and the motor placed behind. But even with the vertical axis moved close to the edge, there still wasn't enough room to pick up the build plates from the far right printers without hitting the vertical axis. To fix this, I moved the X-axis linear rail to the back of the extrusion, right across the motor pulley. And after redesigning the bracket that connects the X-axis belt, the vertical Y-axis became much more flexible, and now the build plate can be picked up correctly. To avoid any risk of the grabbing axis dropping during a power outage, the build included a stepper motor with a built-in magnetic brake. This brake locks the motor when there is no current. There's also an encoder module to recalibrate any missteps. For extra safety, the vertical axis is driven by a lead screw with a high pitch, instead of a belt like on the X-axis. All custom parts, like brackets and motor mounts, I designed with both design for manufacturing and design for assembly in mind. To support the grabbing axis, a linear rail guide is added on the opposite side of the axis. The Z-axis itself uses a smaller linear guide to drive the grabber, and the front end has a small wheel to support the extended weight. This reduces stress when the grabber is holding a heavy part. The grabbing mechanism is also using lightweight aluminum profiles, or extrusions, so it can be adjusted and calibrated after the design phase. The end bracket has a small housing for both the stepper motor and the Hall effect sensor, which works as an end stop. The sensor defines the Z-axis limit and is also used for the homing position. You can see the sensor here, and for the Y-axis it's located here. All these end-stop sensors are normally closed, so if a sensor fails or if the cable breaks, the system will shut down automatically. And finally, instead of a motorized grabbing tool head, I saved a lot of weight by designing a passive grabber instead. Here's a quick demonstration of how it works. When the gantry reaches its target, the grabber extends and places the build plate onto a spring-loaded screw mechanism that locks the plate securely in place. To disconnect, the gantry simply lowers the Y-axis by 15 mm. This lets the grabber release itself from the build plate, and now the gantry can continue with the next step. Since I handled both the programming and the mechanical design of the gantry, I could implement both aspects in the solution of the grabbing mechanism. Thank you for watching.